Yeah, so first I'd like to thank the organizers, Thomas, Elio, and Lara for organizing this wonderful workshop. I really enjoyed it a lot and learned a lot, both from the talks and from discussions. See if I can I just use this as a laser? Yeah, mine gets confused with the Zoom, I think. Okay, so I just do this. Okay, yeah, thanks. So yeah, I changed the topic of my talk. This is a new work that I haven't spoken about before, so I'm really grateful for any input you may have. And it's inspired by the kinds of things that we heard about before, as we heard. There are all sorts of new and exotic 2D systems that show a striking variety of correlated phases. And of course, because they're strongly interacting, they're not easy to understand. And we stumbled across a very simple instance of that displays some of this physics, and maybe we can use it as a test board to some of our theoretical understanding. So this is what this talk is going to be about. Let me start by acknowledging my collaborators on this work. So oh wow, Vladimir is a student at Stanford. Steve Givelson from Stanford. Agnes is currently a student at ETH. If you're looking for really a brilliant postdoc, you're out of luck because Agnes is going to Flatiron Institute, but Vladimir is still not attached. So I encourage you to look into him. And Sebi Huber from ETH. This work started when I visited ETH and chatted with Agnes and Sebi. Yeah, it's this paper has just been posted and would appear on Monday. Okay, so one of the sort of most elementary problems in correlated in interacting quantum many bodies physics is the problem of the homogeneous 2D electron gas. As we all know, it's important both at the fundamental level and for applications, for instance, for constructing density functional theory. So it's as simple as it gets, just a 2D electron gas with a finite density of electrons interacting via Coulomb interaction. And there's only one parameter in the problem. Okay, so it's basically the density of electrons. It's convenient to express it in terms of RS, which is basically the distance between electrons measured in units of the effective Bohr radius, or it's the ratio between Coulomb and kinetic energy. Now, at large RS or even RS of order 1, as we all know, this is a very difficult problem. But nevertheless, people have worked on it very, very hard, and we know quite a bit. This is the state of the art. So it's basically a quantum Monte Carlo, which unfortunately is not exact. It's variational, but nevertheless, it's believed to be quite accurate. Okay, people have improved it over the years, and the results seem to more or less converge on an answer. So these are the energies of different states as a function of RS. And it's believed that there's basically a direct transition. Okay, maybe the physics close to the transition is a little bit complicated, but at 0th order, a transition from a paramagnetic fluid to a Wigner crystal, where the spin ordering of the Wigner crystal can be antiferromagnetic or ferromagnetic. And this happens at an RS value of a little bit over 30. Okay, and interestingly, you would think that one of the things that strong correlations would like to do, for instance, is just polarize the spins, store ferromagnetism. This is believed not to quite occur in this problem. Okay, the ferromagnetic fluid is never the ground state. It's close in the vicinity of the crystal to Fermi liquid transition, but it's not the ground state. Okay, so that's very simple. Electrons with a parabolic dispersion, really as simple as it gets. But as we know, in the last decade, there's really a striking development in the field. We know how to engineer various 2D electron gas systems with really remarkable richness. So, and we heard about some of them in this conference. Pablo just talks about a twisted bilayer and n-layer graphene. There's also crystalline graphene we heard about earlier in the week, and various multi-layer TMD systems. Okay, and these systems have new features compared to the simple 2D electron gas. They're all 2D electron gases of some sort, but they have these new elements. First of all, they're multi-valley systems. They have anisotropic dispersion, not just parabolic. Some of these systems incorporate the Monaro lattice that we heard about, and in some of them there's a large Berry curvature, and so on. Okay, and these features give rise to a extremely rich phase structure. Okay, including all kinds of things that we would never find in the simple 2D electron gas, such as a spin in orbital itinerant ferromagnetism, correlated insulators, superconductors, and even integer or even fractional Chern insulators. A fractional Chern insulator was recently found in one of these multi-layer TMD systems. Okay, so this is, of course, a really wonderful development in our field. But as theorists, this is, of course, extremely challenging. And what I'd like to do in this talk is sort of take one step, okay, beyond the homogeneous electron gas, almost the simplest imaginable generalization of the 2D electron gas, which is a multi-valley 2D electron gas with anisotropic dispersion. So this incorporates some of these features of these this vast variety of new systems. It has two valleys. It has actually strongly anisotropic dispersion in each valley, but it doesn't have a Berry curvature. There's no Monaro lattice, and so on. And the question is, can we understand even the phase diagram of this very relatively simple system, and maybe try to borrow some of the insights to these more complicated and interesting systems that were discovered recently. And luckily, there's actually a realization, a beautiful realization of this kind of model. Okay, so this is a aluminum arsenide quantum well, which can be made extremely clean. Okay, so competitive, but maybe not quite up to the standard of gallium arsenide quantum wells, but still very, very clean. This was developed by Mansour Shaigan's group. And moreover, compared to gallium arsenide, the effective mass is maybe an order of magnitude bigger than in gallium arsenide, which means that we can access the strongly correlated regime at higher densities. Okay, so we can reach the same values of RS at higher densities when the impurities are still quite well screened. Okay, and moreover, there's this important parameter. Okay, so this is a system that has C4 symmetry when rotate by 90 degrees. The two valleys map into each other. The valleys live in the X and Y points of the Brillouin zone. Okay, this is actually the 3D Brillouin zone of aluminum arsenide. When you put it in a quantum well, this Z pocket is pushed away from the Fermi level. So there are two pockets for the 2D dispersion. This is what the 2D Brillouin zone would look like. Okay, so two Fermi surfaces that are related by 90-degree rotation. Each one of them is anisotropic, but of course the anisotropy changes sign between these two valleys. And it turns out that the ratio of the effective masses is quite big. Okay, so this anisotropy is quite large. It's about a factor of 5. So it's really quite extremely eccentric ellipse, the Fermi surface in each one of these valleys. Okay, so moreover, recently, in Shaigan's group, it was discovered that around RS of 20, the system actually breaks the valley symmetry spontaneously. Okay, they believe it's fully valley polarized. This is a measurement using a piezoelectric substrate. You just look at the resistance in the X and Y directions as a function of strain. And what's plotted here is the resistance in these two directions. You see that it's isotropic up to this value of density, which corresponds to RS of around 20. And then you see this jump in the anisotropy. They interpret this as being valley polarization, okay, actually full valley polarization. And you see this very interesting and rich phase diagram. As you lower the density further, the system eventually becomes insulating. Okay, this valley polarized regime is metallic. It eventually becomes insulating. They believe that it goes to a Wigner crystal around 30 something, RS equal 30 something. Okay, and maintains the anisotropy. The insulator is actually also strongly anisotropic in terms of its resistance. And it also becomes spin polarized, that they know by the effect of an in-plane field. Okay, so I'd like to analyze this this problem. Okay, so this is what I'll be talking about. This type of 2D electron gas with two valleys with elliptical Fermi surfaces with this anisotropy parameter. So before in the 2D electron gas, we only had one parameter to vary, which is Rs. Now we'll treat this extra parameter eta, which is the mass ratio. Okay, it would be useful for my purpose, even though it's not there in the experiment. Okay, so I'll introduce a gate, okay, or in fact a dual gate that screens the long-range Coulomb interaction to a varying degree. So D is the distance to the gate that controls how long-range the Coulomb interaction is. And I'll be using this as a theoretical parameter. Okay, the realistic system is somewhere here. The distance of the gate is very, very large. So basically unscreened Coulomb interactions. Okay, and what can we do? So of course, as theorists, we try to expand around various limits. So we can try to understand this problem starting from a smaller s and see what happens. We can start from the Wigner crystal, do a strong coupling expansion. It would turn out to be useful to look at the case where the interactions are short range, when the gates are very, very close. Okay, so this is the dilute limit. Basically, the range of the interaction is much smaller than the distance between particles. This is not the regime the experiment is in, but that's a regime where one can make theoretical progress. And finally, if we want to access the actual experimental regime in the metallic phase, but for RS big, we'll have to resort to numerics. So we'll do some variational Monte Carlo. And interestingly, all these different limits I'll try to convey point to a very strong tendency of the system to break the valley symmetry, or at least to become anisotropic. Okay, so this is the Hamiltonian. Okay, so we have two valleys labeled by this index tau, which is plus or minus 1, and the dispersion is parabolic, but it's anisotropic, and the anisotropy is opposite between the two valleys. And this is the interaction. It's just this Coulomb interaction screened by this dual gate at distance plus and minus d. Okay, there are various effects that we're not taking here into account. There's no electron phonon coupling, no spin orbit coupling, and importantly, no inter-valley scattering. Okay, we're treating these valleys just as indices. This picture is really not to scale. In the true Brillouin zone, the size of these Fermi surfaces is tiny compared to the size of the Brillouin zone, and we're neglecting large momentum transfer scattering. Okay, we're only allowing small momentum scattering, which is to say we're only taking into account the long-range part of the Coulomb interaction. We've actually looked at all of these effects, and they turn out to be small. Okay, so spin orbit coupling may do something. So the idea is the long-range Coulomb interaction is by far the biggest interaction in the problem. However, it turns out that the energy differences between different states also turn out to be a small fraction of that. So we really have to worry about all these terms. We checked. The only one that may be playing a role is spin orbit coupling. Maybe I'll comment about that later. Okay, so of course, we don't expect Hartree-Fock to work very well at intermediate and large RS. Okay, it's a strongly correlated problem, but nevertheless, it's you can gain some insights out of doing that. Okay, so this is a result of a Hartree-Fock mean field calculation for this problem as a function of RS, namely density. Okay, so density becomes lower when RS is bigger, and this anisotropy parameter eta. Okay, so 1 means that the Fermi surfaces are circular, and when you increase eta, they become more and more eccentric. Okay, so you see this cascade of transitions. Okay, you start from a fourfold symmetric case, a symmetric state, and you remove the different flavors successively. Okay, you go to a threefold symmetric, twofold symmetric, one full symmetric. Okay, so now the values of RS, the critical values of RS are of course completely off compared to the experiment. Okay, much, much smaller. Hartree-Fock really likes to break the symmetry. That's the only way for Hartree-Fock to reduce interaction energy. Okay, so overestimates ordered phases, no big surprise there. There's some interesting features of this Hartree-Fock solution. First of all, in this half metal regime where you remove 2 of the 3 flavors, you actually find that the system within Hartree-Fock just can't decide between a spin polarized and a valley polarized phase. They have exactly the same energy. Now, these 2 states, of course, are not related by any symmetry. So this is sort of an accidental degeneracy that we expect to be lifted once we take correlations into account. This is already a hint that in this problem, correlations really play a crucial role. And another feature of the Hartree-Fock solution is that we have the bare anisotropy of the single particle dispersion. That anisotropy is strongly renormalized by interactions. Okay, the interactions really like the Fermi surface to be more circular. And we find that the Hartree-Fock Fermi surfaces are almost circles when RS is substantial. Okay, so I'll actually start from the numerics. That's instructive. So instead of Hartree-Fock, I'll do a variational Monte Carlo. Okay, so this is a well-known technique in the context of the 2D electron gas. So what you do is you write a Slater determinant wave function, and you introduce correlations into it in 2 ways. The first way is a Jastrow factor. Okay, so just a positive factor that suppresses the wave function when any 2 electrons approach each other. And second is this so-called backflow transformation. You evaluate the Slater determinant not quite at the coordinates of the electrons, but at these functions of coordinates of the electrons. It's called backflow because it somehow builds in extra correlations. If one electron moves, the other electrons make way. Okay, and the important thing is that this factor allows you to move the nodes of the many-body wave function. Okay, if you didn't have this factor, the nodes of the many-body wave function, since this is a non-negative factor, would be exactly the same as the nodes of the Slater determinant, and this flexibility to move the nodes around is important. Okay, and this is the phase diagram. Yes. Yeah. So that's a variational wave. That's a variational function that we just optimize over, and it has a functional form that is complicated. We can look at that. Okay, so this is the variational Monte Carlo phase diagram. Okay, so this is again same axis. This is the function of RS. It is a function of the anisotropy of the single particle dispersion, and you see 3 phases here. Okay, the green is the symmetric phase, just the paramagnetic fluid. The yellow is a spin and valley polarized state. So it's a state in which you only pick one valley, one spin, and completely polarize the system there. And this blue region is a fully valley polarized, spin unpolarized state. Okay, so it's a state where you pick one of the 2 valleys, put all of your electrons there. And this dashed line over here, this gray line, is what we believe is the realistic value of eta for aluminum arsenide. So an anisotropy factor of around 5. So you see that around RS equals 12 or 13, we have a transition between the symmetric state and the valley polarized state. Okay, and then there's a big range of RS where we have the valley polarized state as the ground state. Eventually, it goes into the spin and valley polarized state. And we didn't consider the Wigner crystal, which we believe should be somewhere out here, but we don't know. We haven't calculated the energy of the Wigner crystal here. Okay, so you should contrast that. You see this very striking effect of the anisotropy. If the anisotropy factor is 1, you basically never get any polarized phase, neither valley nor spin, up to an RS of around 30, okay, where we believe the Wigner crystal is. So somehow this anisotropy is very, very favorable to these symmetry broken phases. And in particular, it really likes to valley polarize. Okay, so that's the upshot of this calculation. These are some energies as a function of either RS or eta. Okay, so you see, for instance, the fixed RS, if eta is equal to 1, isotropic Fermi surfaces, as we expect, the spin and valley polarized phases, which are these two curves, are exactly the same, but they split very, very rapidly as a function of eta. This is the aluminum arsenide value, and it favors the valley polarized state. Okay, the other thing to note here is the scale. Okay, the overall typical energy scale for the Coulomb interaction is maybe 5 millivolts. Okay, and you see that the typical scale for the differences between these different states is maybe 0.05 millivolts. Okay, really small fraction of the full energy. Okay, so how do we understand this? Okay, so why does anisotropic dispersion like so much to valley polarize, to actually break the symmetry? So we can resort to analytic expansions in special limits. Okay, the first thing we can consider is small rs. Okay, so weak interactions. Now, of course, at small rs, we'll never get any kind of polarized phase. The ground state would be the fully symmetric paramagnetic fluid, but we can still ask which is bigger, the spin or the valley susceptibility. Okay, and or if you like, which kind of order is less disfavored? Is the spin order or the valley order as a function of eta? And it turns out that there's a very simple answer to that. Okay, you do RPA. This is the first term, just the Fock term. This term doesn't distinguish spin and valley. That's why Hartree-Fock gives that their energies is the same. But already at the second order, this is the correlation energy. You find that once the dispersions are different, these are the polarization functions of electrons in valley tau and tau prime. And you could easily show that this number is always bigger when the dispersions are the same, namely that when the two bubbles are evaluated at the same valley relative to different valleys, there's a minus sign in front. So you always gains more correlation energy if all the electrons go to the same valley. Okay, and this is just a second order term, but you can actually prove this for the full RPA energy. Okay, so RPA always favors valley polarization. And this is sort of interesting because it's totally general. It actually doesn't rely on the specific form of the kinetic energy. Anisotropic dispersion, different for the two valleys, in terms of correlation energy, would always favor valley polarization over spin polarization or something else. Okay, the other limit which we can control analytically is this dilute limit. If we artificially imagine that the gate is very close, such that the distance to the gate is smaller than the distance between electrons, okay, we have short range interactions. So this problem has a long history. We know how to solve the electron gas with short range interactions, or 3D electron gas. Okay, what you should do is really, you should first solve the two particle problem. Okay, you should just solve the two particle scattering problem that you can solve exactly. The particles are so dilute that they hardly ever interact 3 at a time. They always interact 2 at a time. So you solve the two particle scattering problem exactly. You use this as your effective interaction, and then you need to solve the new many-body problem with that effective interaction. Okay, and this can be done, and there are two types of interactions. Okay, so there's the two particle scattering amplitude for 2 electrons in the same valley, and a two particle scattering problem for 2 electrons in opposite valleys. Okay, and this eta parameter is again the anisotropy of the Fermi surface, and immediately you see from here that the scattering of the scattering amplitude for 2 particles in different valleys is always larger than the scattering of 2 particles in the same valley. Okay, this means that effectively two particles in opposite valleys interact more strongly than 2 particles in the same valley. Okay, or another way of saying it, the interaction is screened. Okay, if you go to strong interaction, what this denominator describes as screening, the screening is much more effective if the 2 particles are in the same valley. Okay, and from this you can choose a certain order of limits where you can basically make the inter-valley interaction parametrically large and the intra-valley interaction parametrically small. And then you can guarantee that actually from this model with contact interactions, you can actually get that the ground state is fully valley polarized. Okay, so how much time do I have? 2 minutes, yeah. So that's pretty much what I need. Okay, so here's a sort of attempt to have an intuitive understanding why this anisotropy of the dispersion favors valley polarization. Okay, so this is the dispersion in K-space. Now, if we have a finite density of particles, strong interactions, the particles try to avoid each other. We try to localize the particles as much as possible. If we try to localize a particle in this valley, it has a very small kinetic energy in this direction and large in that direction. So in real space, this particle would like to occupy in an anisotropic region that looks like that, and vice versa. Okay, and if we try to fit these particles of both valleys, they don't fit very well. Okay, because one of them is elongated in one direction, the other one in the other direction. It's much more favorable to put everybody in the same valley. Okay, that you can make them avoid each other much more effectively that way. Okay, we know that this is common in nature with elongated objects that interact with each other. Okay, I won't talk about it much. The other limit that we can control is, of course, coming from the Wigner crystal. Okay, so we go deep into the Wigner crystal. We know that because of the long-range Coulomb interactions, the particles would occupy more or less a triangular lattice, and then we can ask what happens to the valley degree of freedom in the 2D electron gas to have any interactions between the spins in the Wigner crystal. You have to tunnel, so that process is exponentially small for large RS. But here the valleys can actually communicate via basically dipolar interactions because of the anisotropic dispersion, and you get an interaction that lifts the valley degeneracy already at order 1/RS to the 3/2. Okay, so this parameter A is just the classical energy of the triangular lattice, and B is basically nothing but the 0-point motion of the phonons of the Wigner crystal. So the phonons of the Wigner crystal induce long-range interactions between the valleys. So what you can do is minimize this parameter B just by solving the phonon dispersion and calculating their 0-point motion energy. You find that the minimum energy configuration is actually this funny configuration. It's not valley polarized, but it is anisotropic. Okay, so this is what's supposed to happen deep in the Wigner crystal for asymptotically large RS. It's possible that there's a transition within the Wigner crystal to a valley polarized phase. We don't know. Okay, yeah, so I'm basically done. Okay, so I've shown the phase diagram of two valley electron gas. The two valleys are related by C4 as a function of the anisotropy. The anisotropy turns out to strongly favor valley polarization. There's some open questions. Okay, the critical value for RS that we get is still quite a bit too small. Okay, 13 compared to 20. And the question is why? I have some ideas. Of course, it's possible that just our variational wave function is not accurate enough, but there are other possibilities. And we'd like to sort of borrow some of these ideas to the more interesting, to the electron gases that we've seen in this conference. So yeah, thank you very much.